In this lesson, we're going to consider the main concepts from section 12.3 about contour diagrams. You're looking at right now a typical contour diagram, which is a topographical graph. We've placed it on a two-dimensional surface, but it's representing the height in 3 dimensions. Each of these little numbers here, let me just highlight one of them, represents a z height. So for instance, this 1700 here, all along this line, all the way around, has a height of 1700. That's called a level curve because all along that curve your altitude is 1700. Now they don't have lines on all of these, but as you have these concentric curves, what happens is you basically have a peak. And so we can see a number of peaks on this. Supposedly, I suppose it could be a valley too if we don't know the numbers, but more likely peaks. And then we have this area in here where we see the lines are really close together and pretty much parallel. And when you have something like this, you have some kind of either, oops, this straightens it out for me all the time, but let's try that again. You have either a valley or a ridge that's going along here, but what you do know is it's quite steep because when the lines get closer and closer together, that means your altitude is changing that much quicker. So the closer your contour lines, the steeper. When you get circles like this, you're coming up to a peak. So let's look at a few other features. So we already talked about the mountain peak right there. This is an example of one with what they call a pass through 2 mountains. Now what's interesting about this one is if I was traveling in this direction, you would see that I would be going down 800, 600, and then 700, 800. So I'd actually be going downhill and back up. So in this direction, it's a valley. But look at the opposite direction. If I go in this direction, 300, 500, 500, 300, I'm actually going up a hill and back down. So this is an interesting point here. Let's get a third color in here. Right here is called a saddle point, and you may learn about this when you take future classes. It's a saddle point, imagine a saddle like on a horse, where you have a point here which is in one direction a minimum and in the other direction a maximum. Over here we've got parallel lines. Parallel lines, like we talked before, represents a long valley. And then the last one here is impossible because right here we have a spot that has an altitude of both 200 and 100 at the same time, which is clearly impossible. So our contour lines with different numbers can never intersect with each other. Now, contour graphs could be more than just topographical maps. In fact, you've seen these on the weather station all the time. Um, Basically, they take the two-dimensional map, say, of Minnesota, and so that's already two-dimensional. And then on top of that, they have values, and it might be for wind speed, it might be for the amount of snow, the amount of rain, or temperature. So all of these different situations. Now in this next example, we have something even different because it's not about on the XY axis a position on a plane, it's 2 variables. And so in this case, our 2 variables are rainfall and temperature. So here on the x-axis, we have rainfall, and here on the y-axis, we have temperature. So let's just consider what this point they gave us means. And it tells us basically that if we are getting 15 inches of rain and our temperature is 76 degrees, we're going to get 100% of our corn production. So what would, I guess 100% of what's presently we're getting. Now it turns out that's not the only combination that gives us 100%. 15 and 76 gives 100%, but so does 18 inches of rainfall and 78 degrees. And you'll notice as the temperature goes up, it seems we need more rainfall. And so we've got this whole band that all has the same values. Now what's also interesting is we can go along this graph, and for instance, let's say we keep our temperature constant. And as we go across here, what happens to our graph? Well, as we go across at 76 degrees, it's not real good if we only get 6 inches of rainfall because we only get 40% of our production. So as the rainfall increases, our the amount of corn production we have increases until we hit really an optimal over here, and then we start going back down, okay? So there is such a thing as too much rain, and so once we get past it, it would appear about 21 inches of rain. Now we're getting too soggy and things get worse. So more rain is good up to a point. In the other direction, let's say our rainfall stays constant. Let's go with, say, 12. And we go up here and we see what happens if we keep rainfall constant. All right, well, let's see. If the temperature is quite cool and we have a very cool summer, we might only get 80% of our production. And at 12 inches, we never hit our optimal, but it does go up, right? So we start down here at 80, and we're going to go up towards 90. And then as the temperature goes up, and this makes perfect sense, without much rainfall, it's going to burn out the crop. And so we can see up here at, say, 90 degrees, we're down to 50% of our production. Now I want to point out we can also estimate values. So let's just go with a point, for instance, let's pick this one right here. No, I don't want that one. Let's do a different one. I want this one right here. There we go. So let's say it's 18 inches of rainfall and 72 degrees. What percent of the production would we expect? Well, if we take a look at this, we can see that we're sitting between two of these curves. We're sitting right here. This curve is 100%. This curve is 110%. I would estimate this to be 105% of the production presently. All right, enough on that problem. Oh wait, we have one more thing to show you. So we talked about this being three-dimensional. We could take this graph and make a three-dimensional model. And so if we actually plotted all of these z values at their appropriate height, this is what it would look like. So we can raise that contour. So whenever you're looking at a contour graph, you should think about how this could be raised to be three-dimensional, because it's really a three-dimensional graph on a two-dimensional page. Now, part of your homework in this lesson is going to be drawing these contour diagrams. So we're going to start with this one, f of xy equals x squared plus y squared. And the first thing you should realize is that f of xy can always be just changed to z. Now, when I draw a contour diagram, I really have the freedom to choose my different z values. But it is important that as you go up, your z values go up by the same amount. So the first z value that I'm going to choose is 4 because I know the square root of 4. And so I know that my radius is going to equal 2, and this is a circle. And so I can draw this on here. So radius of 2, I'm going to draw this circle. And then what I do is I label, this is my z value. My z value is 4. And then I just draw in my circle, and I have my first curve, my first level curve. All right, so since I started at 4, I'm going to go up by 4. So next I've got 8 equals x squared plus y squared. It's another circle, and I know the square root of 8 is something like 2.7 approximately. So I'm going to go up to about 2.7 right there, and I'll get those points in here. And this time, my level curves have a height of 8. So we'll go around, and this won't look too great, but close enough for what we need to achieve here. And then I'm going up by 4 again. 12 equals x squared plus y squared. And I don't have my calculator handy, but I'm thinking, well, that's obviously less than the square root of 16, which is 4. So I'm thinking this is, I don't know, 3 point something, maybe, yeah, 3 points, somewhere between 3 less than 4 and greater than 3. So we're going to kind of just throw it in there. All right, so there we go. There's that one. And this is, I'm going to write it over here because I'm running. They're getting awfully close together here. And we're going to do just one more for good measure, and also because it's a perfect square. So here we go, x squared plus y squared equals 16. This one I know for sure is 4. And so I get this one right here. And notice that every time I draw these, that I'm throwing in my z value. I'll write it back over here again. This is 16. And I want you to notice that our level curves are getting closer together. On this next page, I have a much better looking version of this. This is the same graph. They went up by 2s. It's drawn professionally. But you'll notice here that our curves are getting closer together. So that's important to note. So the curves, level curves, are getting closer together. And when they get closer together, that means that they're also, the curve is getting steeper. So we're getting steeper. And we can see over here, it's actually a paraboloid. And if I took the tangent over here, you can see it's much steeper than, say, oops, let me try drawing that again. My tangent over down here. Let's see if I got, there we go. So we've got all of these, the z values are increasing at an increasing rate, we would say. So our z values are going up, and they're going up at an increasing rate, and so this thing's getting steeper. Okay, we're going to look at another one that's similar. The equation looks quite similar, but as we pick our values, and in this case I'm actually going to start at 1, just because I know what it's going to do. I'm going to start with the square root of x squared plus y squared equals 1. I'm going to square both sides. So that still equals 1. I have a circle with radius 1. And that's a 1. And then I'm going to put in 2. Because I'm going to square both sides. X squared plus y squared equals 4. And now my next level curve goes through the 2's. Like that. Put a 2 in there. And if I do my next one, I'm going to let 3 equal x squared plus y squared. And 9 equals x squared plus y squared. And you can kind of see a pattern here. Now my level curves are, I'll have a height of 3 and my radius is 3. And you should see that they're evenly spaced. So my level curves are evenly spaced. Now think for a moment, what does that mean? All right, here we go. Here's the professionally drawn one. And look at that, we have a cone. And they're evenly spaced because the slope along the side of a cone is constant. It's linear. So when we have that constant rate of change, we're going to have that even spaces between our level curves. All right, we're going to just start off on this one real quick. Level curves for this one, z equals 2x plus 3y plus 1. And when we choose this, I'm going to go ahead and solve this, start solving this for y, because I can see that my level curves are going to be lines. Can you guys see that? They're going to be lines. And so let's just start by making it a constant, just to see what this is going to look like. So I'm going to have 3y equals c minus 2x minus 1, and y equals c minus 2x minus 1 all over 3. Now when I pick values for c, which are really my z values, I want to pick values so that when I plug them in, I can divide by 3. So I want to pick nice numbers because I don't want fractions. So let's start off with letting c equal, let's see. Let me actually just back up for a moment, because the way this looks isn't going to be that helpful to us. Let's take this and write it in point slope form. So negative 2/3 x, and then we've got plus c minus 1 over 3 equals y. Is that making sense now? So I've got my negative 2/3 x here. That gives me my slope. So you can see that every level curve is going to have a slope of negative 2/3. And here's my y-intercept. And so I'm going to pick different values for c that are divisible by 3 here, just for ease of graphing. So for instance, I might like c equals 4. So if I have c equals 4, then y equals negative 2/3 x plus 1. So then I go over here, I'm at 1, and I go down 2 and over 3. And I've got this one. Let's see. We'll just try and draw this. That was bad. Let's try that again. I'm not going to draw beyond there. Okay, and now I want to pick my next value of c. So for instance, I want to go up by 3. You'll see that this works out nicely. So now I've got y equals negative 2/3 x plus 7 minus 1 is 6 over 3 is 2. And see how I'm getting nice numbers. And there we go. That's going to be parallel. And then, I could go smaller. I could say, well, what if c equals 1? Then y equals negative 2/3 x. 1 minus 1 is 0. I like that. So I start at 0, and I'm going down 2 over 1. And we get all of these lines like this. So this had a c value of 1. This one was 4. and this one was 7. All right, so let's look at the really nice looking one. So here's a beautiful looking graph, and you'll see that they picked the same ones I did, 1, 4, 7, and you can keep going. And they're all parallel. Now hopefully you're recognizing what would this graph look like in 3 dimensions. And you should recognize that this is a plane. Now the features of a plane are this. All level curves are lines. And they're not just any lines. They are parallel lines that are equally spaced. So that's how you recognize it from a contour diagram. And of course from an equation, um, we've got z equals ax plus by plus 1. Sorry, I have a general form and not general form, but here we go. So z equals ax plus by plus c. And when you studied this before, you probably had something like ax plus by plus z equals some constant, and you can see how this equation can be rewritten in this form. Oops, plus cz, we'll say. All right, so let's move along to this particular one, and we just want to take a look at what's interesting about this one. Let's just take a little look, and one of the things we want you to notice is look at those zeros along there and the zeros along there and how they correspond here. Right here and right here. And what does that mean for our graph? So those are our level curves at 0. And then you'll see that it goes up on this side and up on this side. And, oh, but look at here. These are negative values. So we've got negative and negative, 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 but over here it's positive. So this is similar to that other graph where we were looking at that if I come across here, I'm going downhill to 0 and then uphill. And here I am actually going uphill and then downhill. So this, ooh, look, I got a neat little star in the middle. That star in the middle is let's see, it's a minimum when I'm going horizontally, and it's a maximum when I'm going vertically. And let's look at our next graph. Look at that. There's that saddle shape, and that point we're talking about is this one right here. Because as we're going along here, it's a minimum. Let's see if I can draw this other one. As we're going along here, it's a maximum. So this is known as a saddle shape. Looks like a saddle. Some of my students have thought it reminds them of a Pringle. So Pringle chip, that is. So yeah, that's important to kind of understand. It comes up on occasion. And then the last thing I just want to talk about is how do you pick your z-values, or just a memory of how to graph different ones. So we're going to take a look at a couple of examples here. And actually, I think we'll leave this for a separate video. I think this is a good place to stop.